Hey everyone, and welcome to today's Explainer. We've got a seriously fascinating topic lined up for you today. We're going to be diving into a phenomenal medical breakthrough that is quite literally hacking the human nervous system to restore a lost sense. You know, we all take our sense of balance completely for granted every single day. But what happens when it just suddenly vanishes? And maybe more importantly, how on earth do we get it back using technology?
I want you to picture something for a second. Imagine the absolutely exhausting, terrifying reality of losing your internal balance so completely that just taking a single step forward makes the entire world aggressively blur and bounce around you. Imagine you're walking down the street and just recognizing a friend's face becomes completely impossible because everything is shaking. It sounds like a literal nightmare, right? But for some people, this is their everyday reality. So, to figure out how science is actually curing this nightmare, we're going to be looking closely at the incredible work of Professor Ali Danesh. His comprehensive lectures and deep clinical research on vestibular implants make up the entire scientific foundation of what we're talking about today. And let me tell you, to grasp the sheer mind-bending complexity of hacking human balance, you need a seriously multidisciplinary approach. And Professor Danesh, well, he's basically a one-man powerhouse for this. He isn't just a board-certified audiologist, he actually operates right at the intersection of communication sciences, biomedical science, psychology, and even electrical engineering and computer science over at Florida Atlantic University. You absolutely have to have that elite understanding of both gooey human biology and hard computer engineering to build a bridge between a human brain and a machine. And that's exactly what he's doing.
All right, let's get right into part one, the devastation of BVL, or bilateral vestibular loss. The ultimate hallmark of BVL is this highly specific kind of torture called oscillopsia. Basically, it's movement-induced blurred vision. Because the inner ear has stopped communicating with the eyes to keep them stable, even the absolute tiniest head movement creates a dizzying, violently bouncing field of vision. Your eyes simply cannot lock onto a target if your head is in motion. It's like trying to film a movie while running without a camera stabilizer. And the real-world consequences of this chronic disequilibrium are just staggering. Because they have zero internal stabilization, patients with BVL face a 31 times greater risk of falling compared to you or me. 31 times. That number represents a terrifying, profound loss of basic physical security. But the crazy thing is, the physical danger of falling is really only half the story. The hidden burdens are immense. This condition severely worsens in the dark, or if you step on uneven ground where your brain can't rely on visual cues anymore. These patients suffer from extreme, constant fatigue and cognitive distraction. Why? Because they have to devote intense, conscious brain power to tasks that should just be automatic. Think about walking down an aisle at the grocery store and just trying to look at a box of cereal on a shelf. A BVL patient has to actively, consciously command their body not to fall over while doing that. As you can guess, this leads to a massive psychological toll, bringing on deep isolation, depression, and severe anxiety. So what do we do about it? Let's move to part two, the solution, vestibular implants. The absolute best way to understand this device is through a pretty simple analogy. It operates a lot like a cochlear implant. You know, the devices that have been treating hearing loss for decades? But instead of capturing sound waves from the air around you, a vestibular implant is designed to capture physical motion. It takes the physical movement of your head in the world and translates it into electrical signals that the brain can actually understand. Let's break down the actual wizardry of how this works. It's a brilliant three-step engineering process. First up, an external head-worn unit uses a super-sensitive 3D motion sensor, a gyroscope, to continuously capture the exact rotational velocity of the person's head. Step two, the internal implant takes that raw data and separates it into three distinct components that perfectly align with the natural axes of the inner ear's three semicircular canals. And finally, step three, it encodes all that movement data by modulating electrical pulses directly into the three ampullary branches of the vestibular nerve. It's literally acting as a bionic inner ear. Now, engineers had to solve a really massive biological puzzle to pull this off. You see, natural vestibular nerves don't just act like simple on and off switches. They have a spontaneous resting activity, a sort of continuous hum. To mimic this biology, the implant actually delivers a continuous, non-zero baseline electrical current, even when the patient's head is completely still. So when the head turns one way, what we call the excitatory direction, the device turns up the pulse.